When we put a forcing function into an ODE, it has to have units of x over t. Thus, the integral of f dt is sort of the total amount of x that was externally added into the system. Let's think about what happens as we deliver a constant amount of total x over shorter and shorter times. We could start with a window of length 1 and height 1. Then we could replace that with a window of length 1/2, but it would have to have height 2 in order to keep the total amount constant. And then we could use width 1/4 with a height of 4, and so on. The idea is that we always keep the total amount added to the system constant, but deliver it over shorter and shorter time periods. We can formalize this idea as follows. Define this function delta sub epsilon as the window function of length epsilon, but having unit area under the curve. Let x sub epsilon be the solution of our linear ODE, with delta sub epsilon as the forcing function. If we take the limit of this solution as epsilon goes to 0, we call the result the impulse response to the ODE. We can work out all the details for this when the coefficient a of t is constant. From time 0 to epsilon, the forcing is at a constant 1 over epsilon. So we need a homogeneous solution and a particular solution that has to be constant. We can easily figure out what that constant has to be. And that gives us the general solution on this segment. Then we apply the initial condition to that, and we find the constant C1. So that's our first segment. For t greater than epsilon, the forcing is just turned off. So we only have the homogeneous solution. The initial time for this segment is at t equals epsilon, and we evaluate the previous segment there in order to get the new initial value. That's used to determine C2 for the second segment of the solution. Now we let epsilon go to 0 in order to find the impulse response. The only part we care about is the second segment, because we're only looking at t greater than epsilon, and epsilon's going to 0. We can actually use L'Hopital's rule to find this limit. Remember, when we do that, since epsilon is the variable in the limit, we have to take derivative of numerator and denominator with respect to epsilon. And you find that this whole limit is just 1. So the impulse response to the problem is e to the at. But hold on a second. That function is also the solution to the unforced version of the problem if we had an initial value of 1 instead of 0. So we found that the impulse response with a 0 initial value is the same as kicking the initial value up from 0 to 1 instantly, and then going on as though there's no forcing at all. let's generalize. To keep with our original delta sub epsilon notation, if we want an impulse at time capital T, we describe that as the solution of the ODE with a forcing function that is delta of t minus capital T. This is usually called the delta function or the Dirac delta function. It doesn't actually behave like a function should, so it's not really a function, but don't worry about that. The key fact of solving a problem with impulse forcing is to just generalize the earlier derivation. So if our forcing includes k times delta of t minus capital T, then the solution gets an instantaneous jump of size k at time capital T. And that's the only effect of the delta. So we can again use a piecewise strategy for solving the problem. Here's an example of a problem with some impulse forcing. The 2 here tells us the time that there's going to be a jump in the solution, and the 3 out in front is the amplitude or the size of that jump. So we have to solve 2 subproblems. The first is the homogeneous problem that includes the initial condition. That's very routinely now just e to the minus 5t. The second subproblem includes the delta and a 0 initial condition. So this system starts at 0 and has 0 forcing for a while. So it just stays 0 up until the time of the impulse. And then once the impulse has hit, we're again at a homogeneous problem, but now with an initial condition where we went up from 0 to 3. So this is an easy problem to solve, and I'm going to put a step function out in front to indicate that nothing happens until jump time. Then the exponential itself also has time delayed by 2 because it starts right there. And then the total solution to our problem is the homogeneous part plus the x1. So to write that out, we have e to the minus 5t plus 3 times the step at 2, e to the minus 5 times t minus 2. So here's a computational solution of an impulse problem, the same one that I did as an example. So in the first part of the solution, we just have the unforced equation with the original initial condition. So you don't even see anything happen until that impulse kicks in at time 2. So here I've solved up to time 2. And now, after the impulse, it's still the unforced equation. But what we've done is we've taken that solution at time 2, and we add 3 to that to become the initial condition for the second phase. And so it looks odd because there's a jump in the solution. It's not continuous anymore, but that's correct. It looks a little bit more transparent if you put this on a log scale, because of course exponential decay is just a straight line. So we have exponential decay, and all of a sudden you inject some more into the solution, but then it exponentially decays again after that.